doing? Good. All right. Well, as she said, I'm Rustin. Nice to meet you guys. A lot of you guys I do already know. As you can see, today we'll be discussing Inside Out. So let's jump right into it. A little overview of our entire presentation. I'm going to talk about basically a nice little introduction, what our project objectives here are, our methodology for creating this digital twin, our preliminary results, what our conclusion is, and then kind of our next steps. So let's go right into an introduction. What even is a digital twin? Well, a digital twin is sort of a real-time virtual counterpart to something that exists, obviously, in the real world, digitally. It can include IoT, Internet of Things technology, so think like maybe real-time light data or electrical data, camera data, something of the sort. And it's really used for analysis and control purposes, which leads into why we even care about making a digital twin. Well, we can do simulative purposes. So think like maybe for missions, maybe a virtual tour, or maybe a fire were to break out, what were to happen here. Monitoring, like let's check our electrical systems, are they all up to standard, are they all up to code? And optimization purposes, maybe we want to introduce a new pedestrian walkway. How would that affect our flow of traffic? So how are we going to go about modeling a digital twin? Well, there's a lot of different ways we could sort of go about creating this sort of thing, but for our route, we're going to use photogrammetry, and specifically, we're going to use photogrammetry in the software called RealityScan. RealityScan is a free piece of software. It's free if you make less than $1 million per year, or if you're an educational institution, and I'm both, so sweet. And how are we going to collect our data? Well, we're going to need to collect data regarding the building, so maybe using a drone, and then walking around with a nice little rover, which will allow us to get really accurate X, Y, and Z data of points, so when we go to remake the model, it's actually anchored spatially correctly. And then maybe for the inside portion, we could use a fancy little SLAM scanner, but those things are like $30,000, and I don't have that. So maybe walking around with some 360 cameras and using some clever tricks might be the way to go. And of course, what's a good testing ground? Well, why not Henson Hall? It's the STEM building after all. And if we can model the building inside and out, I argue that we have a good workflow. So, onto our objectives. I did mention cost, and that is kind of the main portion of this, is that we want a cost-effective modeling workflow. This will allow us to keep everything down, and if something breaks, we can iterate it pretty well. Regarding the drone portion, we're going to be using a DJI Mini 4 Pro. That's going to run you maybe $1,000, and you can see it right there on top of the display case. Again, I mentioned that we're going to walk around with our little rover, but we're also going to use this free online piece of software called Waypoint Map. This will allow us to generate KML files, which are like little flight paths that we can upload into the drone so it can fly what we want. And then regarding the indoor side, we're going to use Insta360 X4 cameras, and specifically 3. You can see the little gimbal I have here. I'll answer questions more about that later. And then we're going to use April tags for the indoor portion. This will kind of act as our indoor ground control point system. And then for pre and post-processing parameters, our software, we're going to use RealityScan, again, for creating the model, but also FFmpeg for tessellating and reprojecting our 360 footage. And then again, this needs to be a practical methodology that is scalable. Again, if we can map Henson, can we map Purdue? Can we map Devil-Vis? Can we map the entirety of campus? That's kind of the whole point of this. And then also of note, this is a part of a broader digital twin initiative. This project really focuses on the modeling aspect, and it uses data that I've done with my other research project, Chasing Shadows, and specifically regarding the outdoor photogrammetry side. So, on to our exterior workflow. Basically, we're going to have to come up with some sort of flight plan. How are we going to even want to capture the data regarding the buildings? Well, using multiple different pathways and heights and elevations and camera angles, we can make sure that we're collecting imagery that covers the entirety of the buildings. So using our east-west pathway here, we're going to do a 90-degree top-down view. This will allow us to collect all the roof data and the surface data below, and then using a north-south pathway here, we can collect a more oblique. This is around a negative 55-degree tilt from the horizon to kind of get the side of the building data, so we're having complete coverage. From there, we're going to walk around with our little rover and get really accurate markers for where certain coordinate locations are, known features, so that we can scale the model later. Then we're going to go do our drone image acquisition. It's as simple as uploading the file, letting the drone do its thing. You can see this perspective here is actually 20 frames of the real data that was collected, and this is the 90-degree top-down view. From there, we do a really cool thing called SFM, structure from motion. This allows us to align the images. The best way I can explain it for most people is you see this little GIF of 3 frames here. Notice how the pole looks different in all 3 of the frames. if you were to scroll through your phone, let's say you just have these pictures on your phone, you can kind of figure out where each picture must be taken relative to the other pictures, just because how the pole looks, and that's sort of a known feature. You can call it a tie point. So that's what's going on behind the hood. But our main processing parameters here, this is within Reality Scan itself. Basically, we're going to upload our data. This is a 10 megabytes of data. This is around 1,200 photos is what we ended up taking. And I have my feature detection set to high. I want to make sure I'm getting everything possible. And I did double our features per megapixel and image from 10 and 40,000 to 20 and 80,000. This is just simply because we have a larger data set and the quality is very high, and I'm trying to ensure that we're capturing everything. But again, image overlap high. You can see most of the prior image and the succeeding image as well. Two more important things of note. Our detector sensitivity was set to high, and that's because these images were shot with very good resolution. There's very minimal noise, so I'm okay with a possible risk of ghosting. And then our distortion model, if any of you guys have done anything with drones, modeling, you'll notice towards the ends of the model, they sort of bow, and that's because of the concavity of the lens. But this distortion model helps it go from this sort of Pringle chip to a more flat-looking model. And then we click align. So, wow, this is our camera positions all aligned in space relative to what it put together, and it generated this very sparse point cloud. Something of note, you recognize this picture from earlier. This picture was actually here in space, or calculated to be there in space. Sweet. We have a nice little kind of broad model, but how can we reference it and scale it correctly? Well, we have our control points. So by going through the software and aligning all of our images to the control points, again, you can see this perspective here is this frame here, and then right there is the control point, which is specifically this little dot on the X here. You basically sit there and go there and you tell the software, hey, this specific pixel is actually this control point. So then when you go to realign it later, it generates actually true to scale reference. And you can see after doing all 5 of those, kind of what images are going to hold together to anchor our model to the correct coordinate plane. So from there, we realign it, and boom, we actually get a really nice model. However, you'll notice that this is actually not a model. This is a dense point cloud. And this is because our model is 161 million triangles. Now, I don't know about you, but my computer would catch on fire if we tried to run that. So this is going to be a major limitation with our project. But hey, we have a model. Okay, quality assessment. How can we make sure this thing is actually lined up correctly? Well, the easiest way is to actually look at our control points. Our biggest error is what, 6 centimeters? That's pretty accurate for our model. Honestly impressive. And then 2, you could generate an orthomosaic, which is a nice top-down perspective, and overlay it in the GIS software. And we can see, yeah, they line up pretty darn well. Something cool of note, this picture was taken obviously before the planetarium. This one was taken after. So you can see the planetarium now with our picture. And that's our exterior workflow. On to the interior. Again, it's going to look fairly similar, but we're going to plan a capture route and then mark our knowns with April tags. Then they have to be within visual line of sight. So obviously this is the first floor plan of Henson. As a little test, we're going to try to map the geography hallway and then kind of like the cafeteria area back here. We could do the map hallway as well, but if we can map one hallway, we can map another hallway. So let's make a cutoff point here and try to map this portion. So establishing a tag-to-tag visual line of sight network. This will allow us to sort of scale and anchor the model. You can kind of think of it as if you were a rock climber flipping in between multiple points. This will allow us to keep everything nice and scaled, and you can kind of see where they are. You can actually go in Henson and see these little QR code looking things. These are what the April tags are. And they use a very similar system called a visual fiducial system. But basically it sees it, scans it, it knows where it is in space. And then we measure distances between the 2 points to give us a sort of distance measurement for scaling. Okay, how are we going to capture our data? Well, we can walk around holding a 360 camera, or we can make a custom rig. So I spent some time over spring break making this nice little custom camera rig, which you can see here. It extends and it allows you to collect the data in the hallway in a very efficient way. You can see me doing that here. This is me holding a little camera rig. And this is actually really cool. This is the actual footage that I used during the processing. But note that I am collecting 360 video, but you're only seeing a certain frame window of that. And we'll talk about that just right after. So again, you're only seeing a certain window of the 360 view. How can we make the software actually see the entire data? Well, we can take the sphere of the 360 video and compress it into an equirectangular image. And so using FFmpeg at Rensu Scripts, it generated each of our possible views. This is our top, middle, and bottom for each of the frames. And I did this at 1 frame per second. It's reasonable. And you can see now our sphere has been all mapped and projected into that little format. Okay, cool. But we need to put it into something that the software can actually understand. So these 90 by 90 windows called a cube map will allow us to see all possible perspectives. Things like 90 degrees here, 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 and back there. And that's what that little cube map is. And you can see it kind of going in real time with all these sort of frames. This is what it's generating. And one important thing of note too, I did run a compression algorithm at the very end. So rather than keeping everything as like a lossless format, each of the cube maps for like 20 gigabytes per like camera location. Running it through like a little minor JPEG compression will keep it down around 300 megabytes. It's going to save us a lot of processing time and file size. Okay, sweet. Let's align everything in reality scan. But there's one small cap. So on to our preliminary results. Basically, we have the data, we have the whole 9 yards regarding the inside portion, but how can we generate one component? The software is generating over 230 different smaller components rather than one large or two large components that are simply anchored together. You can see here in this one, this is actually the lawn side of Devil's, or lawn side of Henson facing like Wacomico and Pocomoke, that sort of area. And this one, looks reasonably well with the sparse point cloud. Here's the entire geography hallway. Did that pretty darn well. But what are we missing? The entire Shore Cafe portion behind, around, the whole 9 yards. And so maybe it could be an alignment issue, could it be a methodology issue. I mean, you can kind of see the cameras are a little bit closer here and more sporadic here. Fun fact, holding this thing for over 2 minutes, your arms will get tired and you start walking faster. So your frame rate, you start losing some data with that. So maybe we need to go revisit that. With the outside portion, again, I mentioned we have a model, but it's kind of the question of how can we even show it, right? This is our dense point cloud here, but going into a model, this is a 5 million triangle model. It's not the greatest. Where you can see there's a ghosting artifact here, and I don't really know what's going on the corner of Henson there. But again, a way of translating it from the dense point cloud to something like this is our current question. And the third thing too, file size and database size. I've only been collecting data for maybe 2 months, and I'm around 300 gigabytes of data, and it's running up very fast. And our processing time too is getting larger or longer and longer. So, on to a nice little conclusion. Basically, regarding the inside portion, we're around, let's say, 60% of the way there. We need to revisit our methodology, but we have so far kind of a good way to, in theory, to make a model. The outside portion, maybe 85, 90% of the way there, right? We have a model, it's anchored, it's tethered, it's correct spatially, but how can we compress it? How can we simplify it for display purposes and actual practicality? So on to our next steps. I mentioned an issue with possibly frame rate extraction with the inside portion, and that's probably another way that we can go about improving it. Maybe upping the frame rate to 2 to 3 frames per second that it's extracting from the 360 video rather than just the one, so that we can increase our data density. Another one, a rectilinear view, so rather than a 90 by 90 window, we'll do a 90 by 180 view, and then do those panning around. So there's more visual overlap for the software to understand. And the third thing as well, maybe April tag density and placement. Do we need more of them or less? And then maybe even going into the actual software itself, an alignment optimization algorithm. Maybe we need to increase, look at our distortion models, or maybe look at what if, is it hallucinating again? Do I have it set to high, medium, or low? Something of the sort. And then for the outside portion, I mentioned model simplification. These are kind of target goals we kind of want to hit maybe per entire model. So for like the desktop, local run, maybe 1.5 to 3 million triangles. The web scene, maybe 2 to 500,000, and then on your mobile, maybe 50 to 150,000. And the third possible opportunity is this really new piece of technology called Gaussian splatting. They use mathematical Gaussians and sort of make them fit all the pictures. You can see here, this one's way more photorealistic compared to our other model. But there's some weird things going on around here, and it's really new, and I'm really unfamiliar with it, but it could be an avenue to go. Because if the Gaussians trained correctly, can actually give a result that's better than our photogrammetry route. So with that, any questions?
Panels for questions, so if anybody has anything to ask Rustin, that would be great.
I got here a little late. Could you restart the first 6 slides?
I'm gonna have to go back a lot, dude. We're at 61, but A little recap is that we're just trying to make a digital tour of this virtual replica of campus. And this is kind of the route that we're going to go about it, but we're facing some hurdles so far.
Have you thought about potentially selling this data to companies like to GrowHub, especially seeing if they've now added those robots that are on there and they would be able to include optimization and stuff like that using this?
Well, no, but in the sense of like regarding the GrowHub robots, they do have LiDAR scanners, sounding scanners, and visual scanners on them as well. They actually probably have a more complete model mesh network of our ground surface than even what I can generate here.
Enormous amount of work. How long did it take you?
To like what, like generate the models or like just come up with the...
Yeah, to test the.
Well, this, I've been, sort of the idea started brewing, I guess, really like in December, and then we kind of got the ball rolling maybe in like February, and so throughout all of my classes, I've just been trying to work on this and iterate this. So I would say really kind of putting my foot on the gas since probably February, mid-February.
So do you have a plan down the road to become entrepreneur since you're handling with gear and everything digital?
Yeah, I mean, it would be really cool to do something with like, I mean, I like really remote sensing a lot, so maybe some avenue with remote sensing, but also like, I kind of really enjoy like the surveying work as well, so maybe even like, I guess freelance surveying or something, maybe getting a professional surveyor's license, that'd be kind of cool. I already have my Part 107, so I can do the drone stuff legally. Yeah.
Okay, very impressive. Thank you.
And while we're doing the next questions, if the next group wants to start setting up, if you have a PowerPoint or anything like that, you can go on up and do that in the background.
Her stuff is preloaded on my computer.
It's
so
already-
it just-
okay.
Yeah.
What caused you to think of doing the 3 cameras in a line on the z-axis rather than just holding one?
Well, if we're holding one camera here, so I guess I'll take this apart. If we're holding one camera at a time, first of all, there's different time increments between each of the models, or each of the runs through. So if I'm holding it like this, right, I could walk here, then I can walk here, then I can walk here, right? But then when you go to align it, I could possibly sway, and now my camera's out here, and now I have a camera perspective here, and a camera perspective here. That's not really doing me too good. But if I have the gimbal all put together, which I'll screw back on here in a second, basically it would keep all of these camera positions aligned along one simple axis. So if for whatever reason during the processing, if it were to calculate a camera perspective to be really far off, I can go, no, I know where you should be based on the other 2 camera perspectives.
All right, we have time for at least one more question, if anybody else has something, or?
Yeah, just use the time. You probably experiment about the image compression, reduce the file size, and then also experiment with what's the minimum amount of overlap so you still maintain. the
I'm trying to
quality.
okay, like regarding I guess the drone side, like maybe like I would say 75–80% is kind of like a good target threshold to not have too much data. I'm already shooting it in 12 megapixels instead of the 48. That lets me get better like I guess frequency of pictures. So rather than 5 seconds between images, it's around 2 seconds, and so it can like 1 speed the workflow up, and 2 I'm still getting all the data I need. The second thing, I'm also like flying closer towards the ground. So like Henson's roof, like let's say is at the highest like 100 feet. I'm flying the drone with the angle perspective at like 105. We're barely making it past those towers. And then 140 from the top down. So it has really good like spatial resolution. I think it's probably like centimeter or so per pixel. But yeah, trying to find a way for the indoor portion, at least with the overlap in that. Because I am walking around. These cameras are recording it in 8K 30. So yeah.
Thank you.
All right. Thank you very much. That gets us to time, and we want to